Section: Introduction. In this section, we focus on improving the quality of large language models, LLMs, by enhancing the quality of their pre-training data. We explore the method of data pruning, which involves selecting a high-quality subset from a larger dataset for training. Data pruning is commonly used to filter out noisy text data. Various techniques are employed, such as importance resampling, deduplication, diversification based on embeddings, and adjusting domain proportions. We specifically investigate the impact of data pruning based on sample perplexity on LLM pretraining. By training a small language model on a subset of the pretraining data and evaluating perplexity for each sample, we can effectively prune the dataset to include samples within a certain perplexity range. This process leads to significant improvements in the final model's performance. Our work differs from previous studies in three main aspects. We emphasize evaluating downstream model quality, explore different dataset compositions, and analyze pruning in non-standard training scenarios. We evaluate the impact of data pruning using meaningful benchmarks, rather than just upstream metrics like perplexity. This approach allows us to draw stronger conclusions about the effectiveness of perplexity-based data pruning. Furthermore, we consider datasets with diverse domain compositions, unlike previous studies that focused on a single domain. We find that the success of pruning techniques varies depending on the dataset composition. Additionally, we investigate perplexity-based data pruning in overtraining and data-constrained scenarios, providing insights for practitioners on when to use this technique effectively. Our contributions include demonstrating that a small reference model can successfully prune the pre-training dataset of a much larger language model, leading to improved downstream performance and reduced pre-training steps. We highlight the sensitivity of data pruning techniques to dataset composition and the potential benefits of using perplexity-based pruning in non-standard training settings. Lastly, we caution against relying solely on test set perplexity for evaluating data pruning techniques, as higher perplexity values may still result in better downstream task performance. Section Summary. In this section, we delve into the realm of improving large language models, LLMs, by enhancing the quality of their pre-training data through data pruning techniques. Our focus is on utilizing perplexity-based data pruning to select high-quality samples for training, showcasing its significant impact on downstream model performance. We explore the sensitivity of data pruning methods to dataset domain compositions, emphasizing the need to evaluate diverse dataset compositions for effective pruning strategies, especially in non-standard training regimes like overtraining and data-constrained scenarios. Section: Perplexity-based data pruning. In this section, we begin by training a reference model to calculate the perplexity of all samples in our dataset. We divide the original dataset into two parts, one for training the reference model and the other for training the final model. After training the reference model on the standard next token prediction task, we calculate the perplexity of each sample in the final model's training split. We then reduce the size of the final model's dataset split to a fraction of its original size, known as the selection rate, R_S, by choosing samples based on their perplexity levels, which can be low, medium, or high. In low selection, we pick samples with the lowest perplexity. In medium selection, we select samples with perplexity values close to the median perplexity, which means samples with perplexity in the middle range of all perplexities. In high selection, we choose samples with the highest perplexity. After pruning the dataset, we train the final model using the standard next token prediction task on the pruned version of the final model training split. We assume that the reference model is much smaller than the final model, which is a practical setup for data pruning in large language models. Next, we conduct experiments using models based on the MPT family of transformer models. The reference models have 125 million parameters, while the final models have either 1 billion or 3 billion parameters. We work with two datasets, the pile, consisting of 22 different domains, and DOLMA, composed of 7 domains mainly from web scrapes. We tokenize all datasets using the GPT-4 tokenizer. For training and hyperparameters, the reference models are trained for 26 billion tokens. The final models are trained to chinchilla optimal, where the training duration is 20 times the parameter count. We use the decoupled Lion optimizer with a cosine learning rate schedule. Training details include maximum learning rates and weight decays for different models. We evaluate the models on 33 downstream question answering tasks using the Mosaic ML evaluation gauntlet. We normalize the accuracy of each task and report the average normalized accuracy across all task categories. Perplexity-based data pruning proves beneficial for downstream performance. By selecting samples based on perplexity levels, we observe improved performance in downstream tasks. The best settings involve selecting high perplexity samples at a 50% rate for the PILE dataset and medium perplexity samples at a 50% rate for the DOLMA dataset. Models pre-trained on the Perplexity-pruned dataset outperform baseline models across all datasets and model sizes. Specifically, Perplexity-based data pruning enhances the average downstream performance for both 1B and 3B models on the PILE and DOLMA datasets. These findings indicate that using perplexity as a criterion for data selection can significantly enhance the performance of larger language models. Section Summary. In this section, we introduce a method called perplexity-based data pruning, where we train a reference model to calculate perplexity on dataset samples. By selecting samples based on low, medium, or high perplexity criteria, we prune the dataset to improve downstream performance significantly, showing that training on data selected by a smaller model can lead to substantial improvements for larger models. Section. Perplexity-based data pruning improves training efficiency. In this section, we explore how perplexity-based data pruning can enhance the training efficiency of models. We investigate whether training on pruned data allows models to achieve similar performance to models trained on unpruned data but in fewer training steps. By comparing the performance of partially trained models from the 1B baseline and perplexity-pruned models, we observe that perplexity pruning consistently outperforms the baseline model during intermediate pre-training stages. The perplexity-pruned models reach the same average accuracy as the baseline models in significantly fewer steps for both PILE and DOLMA datasets. This indicates that using high-quality data from perplexity-based pruning enables faster learning, leading to comparable performance with fewer pre-training steps. Furthermore, we examine the impact of overtraining models on perplexity-pruned datasets. We train a 1B parameter model with 130B tokens, which is 5 times more tokens than the optimal number. The results show that while the absolute gain in performance from perplexity-based data pruning is similar for both compute-optimal and overtrained models on the PILE dataset, the gain decreases for DOLMA in the overtrained scenario. This suggests that while high-quality data from pruning still improves performance in overtrained models, the relative improvement compared to the baseline diminishes with overtraining. Additionally, we investigate how perplexity-based data pruning performs in data-constrained scenarios where the number of tokens is limited, leading to more data repetitions after pruning. Our experiments show that training on perplexity-pruned data provides performance gains for up to 2 repetitions on both the PILE and DOLMA datasets. Beyond 4 repetitions, the performance gains become negligible, indicating that the quality of pruned data does not alter the point at which repeating data no longer significantly improves performance. Section Summary. In this section, we explore how perplexity-based data pruning enhances model training efficiency and performance. By training models on pruned data, we observe that they achieve comparable downstream performance to models trained on unpruned data but in significantly fewer steps. Additionally, we investigate the impact of overtraining models on perplexity-pruned datasets and find that while the data quality improvement from pruning still enhances performance, the relative gain diminishes in the overtrained regime. Section. Upstream perplexity is not a reliable evaluation metric for data pruning. In this section, we wanted to see if using perplexity as a measure for data pruning is a good way to evaluate model performance. Pruning changes the dataset, so models trained on pruned data may not represent the original data well. We compared the perplexity on a test set and the actual performance for models trained on the original and pruned versions of the PILE and DOLMA datasets. Surprisingly, while the perplexity got worse on the pruned data, the actual performance improved. This suggests that relying only on test set perplexity may not be the best way to evaluate data pruning work. It's better to directly test on downstream benchmarks. To understand how perplexity-based data pruning works, we looked at the distribution of reference model perplexities for each dataset. We found that the distribution of log perplexities for the PILE dataset is different from that of the DOLMA dataset. Pruning also changes the composition of domains in the dataset, favoring web-scraped domains over technical domains like code or scientific papers. This shift is more noticeable in the PILE dataset. Traditionally, pruning text data involves filtering out low-quality samples using rules-based methods or n-gram perplexity-based methods. Our approach uses perplexity differently by estimating the difficulty of examples rather than checking if they are in the same distribution as a reference model. Our method complements existing techniques that apply basic rules-based pruning. Recent research has explored using neural networks to intelligently prune datasets by sampling high-quality data or optimizing domain proportions for better learning. While previous work focused on curating data for fine-tuning, we extend this to pre-training datasets and evaluate model quality based on downstream metrics across different dataset compositions. This allows us to suggest that a smaller reference model can be effective for pruning text data. Section Summary. In this section, we explore how data pruning impacts model performance by comparing perplexity-based evaluations with downstream performance for data intervention techniques. We find that while pruning may worsen perplexity on the original data distribution, it can significantly improve average downstream performance, indicating that test set perplexity may not always be a reliable metric for data pruning work. Additionally, we investigate the distribution of reference model perplexities and how pruning affects domain composition, highlighting the need to evaluate model quality directly on downstream benchmarks rather than relying solely on perplexity-based metrics. Section: Data pruning on vision tasks. In this section, we discuss data pruning in vision tasks. We have observed that data pruning is gaining importance due to the vast amount of text data available. It has also been widely used in the field of vision. Researchers often remove data points based on their loss or gradients during training. Additionally, model-based approaches have been employed for pruning image data. It is worth noting that in some literature, data pruning is also known as core set selection. Recent studies have shown that active learning algorithms tend to outperform many data subset selection algorithms, which is quite surprising. In the realm of contrastive learning, hard negative mining has proven to be an effective method for data pruning. Furthermore, there have been investigations into the scaling laws for training on pruned data specifically in the context of vision models.